Hi guys. Today is going to be the first official content that I'm going to put together for Unit 1. I will talk to you, or will have already talked to you, about Chapter 2. We're going to jump right into Chapter 3 here. At the beginning of every chapter, I like to put the I like to put the targets, or the standards that the College Board really would like you to pay attention to, and we kind of hit these. These are kind of statements that are very broad, and we can go into much more detail on each of them. But these are some of the big ideas that you should be able to understand. You should look at this slide and say, at the end of watching this PowerPoint or going through the PowerPoint, you should be able to say to yourself, yeah, I get those, or I can explain those, or I can understand those. Okay? Now, this entire chapter is about water and how it affects the environment, and also biological things or systems that live in this particular environment, or in these particular environments. A lot of the things you already know about water, right? We don't have to go through like the first 6 or 7 slides of this, because it talks about the components of water, which are hydrogen and oxygen, talks about their chemical nature and this, that, and the other. Okay, so we can skip that, I'm assuming, and if you really want to know that stuff, go back and study it. If you haven't learned it by now, then maybe we can get you back into Honors Chem or something like that. But water is composed of hydrogen and oxygen, 2 parts hydrogen and 1 part oxygen. Now, we are going to start to talk a little bit more about some of the chemical nature of water, because that is important to understanding how water actually interacts with life, how water can work with biological systems. Okay, so we are going to talk about the fact that water has a covalent bond, and when we talk about covalent bonds, we talk about the sharing of electrons. Right? Ionic bonds mean that some molecules will steal those electrons, more or less, and hold them tightly away from where they took them from. Whereas covalent bonds means the electrons are shared unequally in this case. Okay. In this case, oxygen takes most of the negative charge. Most of those electrons are pulled towards oxygen, and as a result, oxygen has like a, let's see if I can get this little pen going here. Oxygen has like a positive charge associated with, or pardon me, let's erase that. That will erase by itself. Oxygen has a negative charge because it pulls those electrons closer towards itself. Okay? And as a result, hydrogen, these little white guys down here, is Mickey Mouse looking ears, they have positive charges. Okay? So, when we see this covalent bond, and we see this covalent bond where electrons are shared unequally, it creates this situation where oxygen has a negative charge because it hoards those electrons. It kind of pulls them closer to itself as compared to the hydrogen, which doesn't. And so we have negative for oxygen and positive for hydrogen. Okay? Now, the reason for this is because of the electronegativity of oxygen, right? The electronegativity of oxygen is much higher than that of hydrogen, so oxygen is going to want to grab those electrons and pull them closer to itself than hydrogen will, okay? Which is why we see that partial negative charge on the oxygen as opposed to the hydrogen, which is positive, okay? This results in a situation where we've got a molecule that is polar, okay? And many of the unique characteristics and properties of water arise because of its polarity. And that's something that you have to understand, because we're going to talk about the polarity of water almost the entire year. It's going to continue to pop up over and over and over again. We start to talk about cells, and we start to talk about things entering the cells and leaving the cells, and how certain molecules are needed in, let's say, mitochondria, like water, and how they get across a cell membrane. This idea of polarity is absolutely important, so we have to understand what it means and how it arises. And so polarity arises because there is a molecule that has a positive side and also a negative side. okay? And that's exactly what I showed you with the little pen in the previous slide, is the fact that oxygen, this big red atom right here, has a partial negative charge, whereas water has a partial, or pardon me, as hydrogen has a partial positive charge. Okay, this is due to that unequal sharing of the electrons. And I know this is kind of a silly thing, but think of, we call this a polar molecule because it has two different things going on. It's got two different poles. You think about the north end of a magnet and the south end of a magnet. It's got polarity. Magnets have poles, the north pole and the south pole. You can think of it that way if you want. I always use this really dumb example of, if you're really having trouble deciphering what a polar molecule is, think about, Santa Claus. Okay, I know that sounds weird, but Santa Claus is very, very popular. He's everybody loves him. He's very nice. He brings toys and presents. That's a positive thing, right? Santa Claus is a positive guy, right? And he lives at the North Pole. Okay, so here we go. There's one pole. In this case, would be Santa Claus would be the positive one. Let's go ahead and do this. This guy here again. Do this. Santa Claus. Okay. There's your North Pole where Santa Claus lives. He's polar, he's happy, he's fun, he's nice, right? A positive thing. Whereas on the other side, the negative pole would be like the South Pole. Think about where the South Pole is. Think about what's at the South Pole. Absolutely nothing. It's the most barren wasteland on the face of the planet. There's nothing there. It's not happy. There are times when there's no light. It's blah. It's negative 100 degrees Celsius, whatever it is. It's just crazy, crazy cold and nasty and yucky. Those are all negative things, right? You associate those with negative things. So think about it in terms of that. Santa Claus is positive at the North Pole, and at the South Pole it's negative and nasty and snowy and nothing lives there, right? Okay, so let's on we go. If that was too much for you, or if you already got polarity, the beauty about this video is you can fast forward through it if you'd like. Okay, so let's keep on trucking here. The polarity that we see, causes something known as hydrogen bonding. Okay, and so when we see water molecules, oftentimes we see hydrogen bonds causing those water molecules to interact either with themselves or with other things. Okay, so this polarity begets these weak hydrogen bonds, which are extremely important to biological systems. And we'll talk about, in more ways than just one, we'll talk about how these hydrogen bonds are important to biological systems. Okay, but this causes water to attract to other molecules as well as itself, which leads to some of the unique properties that we see form in water, which is basically what we're going to spend most of the rest of this lecture talking about, is the unique properties of water that arise because of polarity and hydrogen bonding. Okay, those special properties that make it an extremely unique substance are its attractiveness to other things and also to itself. The way that it can help moderate temperature in many different facets, and once we get to that section we'll talk more about how it helps to moderate the temperature. How it, when it freezes, it expands. It's one of the only substances on the face of the planet that actually does this. When you take its liquid form and make it solid, it's one of the only substances where it expands when it gets solid. Okay, so we'll discuss how that plays into biological systems and how it living things, and also its versatility as a solvent. Okay, all of these things are what we would consider to be unique, and one of the reasons that water is such an important substance when we talk about living organisms is, and one of the reasons why when scientists go looking for alien life forms, they always look for places that have water, because they assume water is really important to us. Why wouldn't it be important to alien species? And that's maybe a little bit misguided in my opinion, but we can talk about extraterrestrials some other time. All right, so we're going to touch on each one of these special properties, expand on it, talk about it a little bit more in depth, and then also discuss how it affects biological systems and how it works with living things. Okay. The first thing we'll touch on here is the attractiveness, cohesion and adhesion. We saw those terms on the previous slide, cohesion and adhesion, and basically all these two terms do is they describe how water interacts with other things, other molecules. Cohesion is the attraction between water molecules, okay? Either one molecule and another one, or many water molecules with each other. It doesn't matter, okay? It's the attraction between water molecules. And this leads to surface tension and how we see water actually flow, okay? And one of the things I pointed out here with this picture is the water bug. If you guys have never seen these little water striders, they're actually really, really cool bugs. And they sit on the top of a pond. Okay, so you think about how this guy right here gets around. Okay, how water plays in his everyday life. His entire everything is based on water, and the fact that water can stick together and create surface tension that holds his little body. Right, he can go hunting. Okay, on top of the water. He can go look for mates on top of the water. He lays his eggs, or she lays the eggs on top of the water. You know, all of these different things are needed for this water strider to do what it does in its everyday life, and it's all based on the fact that water molecules actually stick together. Okay, that the attraction between those water molecules by way of hydrogen bonding, again, that's another key term that we've talked about, by way of hydrogen bonding is strong enough, just strong enough, so that this little water strider can bounce around on top. Okay, and it also causes the flow of water, which we'll talk about towards the very end here. Adhesion is the attraction between water and other molecules. The way I always remember the difference between adhesion and cohesion is to think to myself, I've heard the term an adhesive before, right? An adhesive is something like tape or glue, and basically what you use tape or glue for, let's say I take, look at that, that's a flip phone, guys, right there. If we were in person, you could make fun of me, but I have a flip phone. And I use it. It's my primary source of communication. But anyway, let's say I wanted to take this flip phone and I wanted to glue it to my smart board. Okay? I want to glue it to the smart board. I would use an adhesive, right? And the adhesive is glue. All right? So we use the adhesive. And basically what I'm trying to get at here is that I've got a thing, a phone, glued to a different thing, which is a smart board. Okay? And you can think about it in terms of water. Water is a molecule that's glued to another thing, not another water molecule, but another thing. Okay? And so the example that's given here, and you've all seen this before at some point, is when water sticks to the windshield. You see little beads of water all over the windshield after it rains, right? And the reason that it's not sliding down is because the water has some kind of attractiveness. It is attracted to the molecules of the windshield, and that is what we call adhesion. Okay. Now, these two things, adhesion and cohesion, work together in a process known as capillary action. Which, okay, think about it this way, and I'm kind of going into some drastic examples here, but capillary action is responsible for life on this planet as we know it. Okay, I know that sounds like a weird thing to say, and what are you talking about, Sutherland? But capillary action is responsible for plants getting water, right? And if plants don't get water, they die, and if plants die, everything else dies. Okay, it's the base of the food chain. That's how I kind of drew that conclusion. But anyway, capillary action describes the movement of water against the pull of gravity, and that's exactly what we see in this picture over here. We see water molecules going from the ground where the water is held all the way up to the plant's leaves where it's ultimately used, and some of that water actually leaves the top of the plant. Now, the reason that this water is pulled up like that is the same reason. It's actually a really neat little process, physical process. The reason that we see the water move like this is the same reason we get liquid up a straw when we're trying to drink at a McDonald's or something like that. Drink a Diet Coke or whatever from McDonald's. Because this area up here, let me get, this thing's got a neat little option, laser pointer. This area right up here, okay, has a lower atmospheric pressure than this area down here, okay? And so what that does, that creates negative pressure, okay? And it's the exact same thing that happens when you use your mouth to suck on the straw to pull the liquid up the straw, okay? Your mouth is creating the negative pressure at the top of the straw, and the liquid moves up it. It's exactly what we see here, okay? Now that doesn't happen unless water actually sticks to itself and also sticks to other things, okay? And so this is what we would actually see in plant stems, okay? We see water molecules adhering to the edge of what is called the xylem. The xylem is like the little tubes inside the plant stems that carry water. And they also cohere, I don't know if I might have made that word up, cohere, cohes, whatever it is. They undergo this attraction between other water molecules right here, okay? And so what you get is almost like a chain of water. It's almost like uninterrupted water stream, okay? So it causes this water to flow and allows the water to flow from the root down at the bottom to the stems and the leaves all the way at the top, okay? So that negative pressure combined with the fact that water can adhere to the sides of these little phloem straw, or these xylem straws, and also to themselves allows for this interaction. So it's kind of a neat interaction when you think about it. The physical nature of how this water moves and also the chemical nature of how the water sticks to itself and other things is responsible for life on this planet as we know it right now. Okay. All right, on to the next topic. The next unique property of water is the fact that it can help moderate temperature. Okay, and I really like talking about this topic because it describes how water moderates the temperature of many different things. Okay, one thing I'd like to do before we start discussing how water helps to moderate the temperature of things, both biologically and abiotically, is to discuss the difference between heat and temperature. Okay, because we'll kind of use both of those terms, not interchangeably, but when I talk here in the next few slides. Okay, so to get it out of the way right off the bat, heat is the measure of the total amount of kinetic energy due to molecular motion in something, okay? Whereas temperature measures the intensity of that heat. Okay, so when we think about how hot some place is, it's that hot because the molecules in a given area are bouncing off of that area more frequently, and that causes that area or that thing to be hotter as a result, to have more heat associated with it. Temperature is nothing more than the intensity and the measure of that heat. All right, so let's keep on moving on then. Water moderates the air temperature by absorbing heat from the air or releasing it to the air. It works like a heat bank. And so when we think about how it moderates the temperature of things, we've got to keep that statement in mind because the two examples that I'm going to give directly point to this statement right here, the fact that water moderates temperature by absorbing heat from the air and releasing it to the air. Okay? It's like a heat bank, and you have to think about how heat transfers from one thing to another. Heat transfers from one thing to another by going from warm objects to cool objects. And this was always like a mind blower for me, and you guys probably have heard this many, many times, but I always bring it up because it was one of those seminal points in my, I guess, scientific life. I'm like, oh, wow, that's crazy. It's one of those, I guess it's called a discrepant event in teaching, where you show something and then all of a sudden you kind of tell them what's actually happening and it's wrong. I thought, when I was younger, that when you put ice cubes into a warm drink, it was like the ice was so cold and it gives the coldness to the hot drink. And in actuality, it's the complete opposite. The warm drink is actually losing its heat to the ice cubes. Okay, so the warm part of the drink is actually giving up its heat. The heat is passing from this warm object, which is the liquid that you want to drink, to the cool object, which is the ice. Okay? And the reason that we see the ice melt is not because it's giving its ice or coldness to the surrounding drink, but because the heat from the drink is going in and breaking those hydrogen bonds. And we'll talk about ice in a little bit, but breaking those bonds. And so as a result, the ice is sucking the heat out of the drink. Okay, so it's kind of a neat way of reminding yourself how heat moves. And so I want you to try to remember that example if it doesn't. And you know, think about things that your parents say. Right? These are things I say and my wife says because the kids understand it better. You know, especially now it's summertime. Yesterday was 94 degrees. Hey, shut the door! You're letting all the air out. Is that accurate? No, not at all. You're not letting the air conditioning out. When the kids leave the door open, or when you leave the door open, you're actually letting the hot air in, which makes the inside of the house hotter. You're not letting the cool air out. It's not how it works. Okay? So that might be an example you use as well to understand how heat moves. And I think that's going to be an important thing to understand once we start to work our way through how ice and things like that work. All right. So water has what's known as a very high specific heat capacity. Okay, and this is the chemical number associated with it: 4.18 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. That basically just tells us how much water, or how much heat that water can absorb without changing temperature, or how much heat it can absorb and still change a certain amount of temperature. And it turns out that water, because of this number, can absorb a lot of heat without changing a whole lot of temperature. Okay, so you can dump a lot of heat into a little thing of water, and it's not going to change the temperature very much. Okay, which is why we consider water like a heat bank. It's like you can dump all this water in there, or this heat in there, and it's not going to raise temperature hardly at all. Okay, now you can continue to dump more and more and more and more heat in there, and eventually the temperature will raise, and that's what this figure gives us. That's what this figure tells us. It gives us a specific amount of heat. Okay, whatever you want to measure heat as, joules or calories, a specific amount of heat per gram of water will raise it 1 degree Celsius. Okay, so 1 calorie of heat energy will raise 1 gram of water. If you weigh it, you put it on a scale, and you weigh 1 gram, will raise 1 gram of water 1 degree Celsius. That's what that term means. And so that is comparatively high when you compare it to things like, let's say, I'm looking at the periodic table on the wall right now, something like gold, right? Gold has a very low specific heat capacity. Other metals that you might think of have a very low specific heat capacity. Aluminum. I could hold, this is a lighter. I'm assuming that this is made out of aluminum or some kind of something like that. If I were to turn this on and leave it on, I would eventually feel the heat down here where I'm feeling it, because it's heating up the tip, and then where it's hottest, up here, is going to cause that heat to move down here where it's cooler. And eventually I'll feel that. Okay, I'll feel it down here. And the reason it does that so quickly is because the specific heat capacity of aluminum, for instance, is very, very low. Okay, it's going to heat up a lot quicker than, let's say, water. Okay? So this feature of water allows optimal conditions for life on Earth in many parts of the Earth that are otherwise be uninhabitable. This is a picture of a microwave. It's there for a reason. I've kind of stopped telling that story. If you really want to know about it, you can ask about it in class tomorrow. But right now, we're going to skip it and talk about something a little bit more applicable to what we've been messing with. Okay, this is a picture of Southern California, and it's here to illustrate how water helps to create situations, or how water helps to create areas in which there is uninhabitable terrain, and then all of a sudden makes it so that terrain is habitable. Okay, how we take an area that would be really, really nasty without some water next to it and basically allow for some kind of habitable condition. Okay, so what we see here is Southern California. I've never been to Southern California, but I've been told that this picture is relatively accurate in terms of temperatures at these distinct places. People who go to San Diego tell me that it's almost the exact same weather every single day. Okay, like 75, 80, and sunny. Okay, people who've gone to Los Angeles, and I think it's a little bit hotter in Los Angeles, but have said that the weather in Los Angeles is relatively pleasant. Same thing with Santa Ana. Now, if we look, let's say this is no more than, let's say we take from this point here at San Diego and just go straight east, sorry. That's maybe 40 to 60 miles, okay? So Palm Springs is about 40 to 60 miles inland, right, away from the water. And we look at that, Palm Springs 106 degrees. 106 degrees. That's a temperature difference of 34 degrees. 34 degrees. That's a ton. That's a ton. Think about it this way. We've experienced drastic temperature differences, but not like an everyday temperature difference. But think about it this way. Let's say you play soccer, right? And you've got a game, let's say in maybe Danville. Okay, that's maybe 60, 70 miles away. So it's probably a little bit longer than that, but for example's sake, we'll say it's 60 or 70 miles away. Let's say it's in the springtime and you play your soccer game, and here it's 55 degrees. Like, oh yes, 55 degrees. It's going to be a great day for soccer. And then you go to Danville, and all of a sudden it's 90 degrees. Okay, that's a difference of roughly 34, 35 degrees. And that's not pleasant. That's not pleasant at all. And so think about it. The reason that San Diego is as pleasant as it is because of this giant body of water called the Pacific Ocean off its west coast. It makes this area, which would otherwise be, Southern California is really far south. It's farther south than a lot of you guys probably think it is. And if this giant body of water wasn't here, San Diego would probably be closer to 108, 110 degrees on a daily basis as opposed to 72. Okay? Take a look on a map. It is close to Mexico, and we know how hot Mexico can get, and different parts of Mexico can get. But since it is right on this coastline, it is right next to this giant heat bank, that allows for San Diego to be habitable. You wouldn't really want to live there. I know people live in Palm Springs and people live in the desert and whatever, but it's not pleasant. Like, you wouldn't want to live in a place like that unless you really, really like the heat. I wouldn't anyway. And here we notice it's all of a sudden it's very habitable. That's because you've got a lot of water. The Pacific Ocean is a lot of water. Okay, and again, look at a map and see how much water is in the Pacific Ocean. So you think about the heat that would be on land right here in this kind of tan area. How much heat would normally be there? That heat kind of gets sucked out into this giant body of water. It gets absorbed by this giant body of water because, again, think about how heat moves, right? It moves from this area that's very highly concentrated in heat, high heat area, to this area that's low heat, which would be a big body of cool water, right? So the heat is just naturally going to move out into this area and be absorbed by the ocean. Now, the other thing that's really neat about the ocean is that it moves, right? This is not just a stagnant body of water. There's currents, and what's going to happen is it's going to take that heat back out here, out to the greater part of the Pacific Ocean, and gets more heat from the coastline, and then it takes it out. Gets more heat from the coastline, takes it away. So these currents that we see continue to move that water away from the land. And so it's not going to be left to sit there and make San Diego hot again, okay? Now, this is also combined with a phenomenon we have yet to talk about called the heat of vaporization. Okay, the heat of vaporization basically just means the heat at which something turns to a gas. Water also has a really, really high heat of vaporization compared to many other types of substances, okay? And one of the things that you'll notice is that it can take a lot of heat without turning into a gas. Okay, so that combined with the fact that the heat moves into the Pacific Ocean, combined with the fact that it takes a lot of heat for it to actually cause the Pacific Ocean to evaporate, means that it's not going to evaporate, right? It's just going to keep taking heat and keep circulating that heat out into the greater Pacific Ocean. And so this type of phenomenon helps to moderate the Earth's climate as a whole, make the Earth's climate relatively easy for us to live pretty much anywhere. Okay, so I've probably spent more time on this slide than I need to, but you can always fast forward through it if you thought it was boring or think it was going to get boring. Okay, so let's transition now to organisms. How does water help organisms to modify their heat? Organisms have the heat in their body moderated by sweating. Okay, we call this in the scientific community, I guess, evaporative cooling. Okay, other people call it sweating. And I'm going to try to draw on this. This is better when I can draw it on the board. But this, let's do this, and I'm going to get rid of this. All right. So think about this. This is my skin. Okay. This is a bead of sweat, okay? Think about what happens when, keep that picture in your mind, think about what happens when you sweat, right? You are covered in these beads of sweat all over your body. And it's really uncomfortable because the reason that you have started sweating is because your body temperature is increased because you're playing soccer, playing football, or whatever, or marching band. Any of that stuff during summer months can cause you to sweat and cover your body with these beads of sweat, which are essentially water. All right, so you are now covered in this watery substance, and we have to think about how heat moves. Right, we got to think about how heat moves. Let me draw my skin there again. Draw this bead of water. Heat moves from something that's hot, which is the body that just got done working out, into something that's cooler, which is the water that the body just produced. So these arrows represent heat, okay? And they go into the water, okay? And so what do we know about water? It has a high heat of vaporization, and it has a high specific heat capacity. So this high specific heat capacity allows it to take in a bunch of heat, okay? So the sweat is taking in a bunch of those arrows of heat before it's actually going to raise any degrees of temperature. Okay, so that's one thing that your sweat does for you. It sucks in a lot of that heat from your body, and it takes a lot of that heat to actually raise the temperature of the water. Okay. Number two, second thing this sweat does for you, it has that high heat of vaporization. So it will continue to suck in that heat more and more and more and more and more and more until it reaches, those little beads of sweat reach that level of the heat of vaporization of water. And once they do, then they evaporate, then they leave you. And you notice eventually your body, the sweat evaporates, right? It's because it's absorbed enough heat from your body to do so. And one thing you'll notice, and just sit down and think about it next time you work out, and you work up a really good sweat. It's really disgusting and uncomfortable and nasty, right? I do this sometimes when I'm mowing at my house. I'll be pouring sweat and I'll just sit on the front porch. Okay, I'll just sit on the front porch. I'll still be outside, and eventually, if I sit long enough, I start to feel like cold and clammy. If you've ever just done that, before you don't go inside and dry off and get in the air conditioner, just sit and let that stuff naturally evaporate from your body and feel how cold and clammy you get. It's the weirdest thing, but that is what is happening here. Your body has had all of that heat sucked away from it by the sweat, and then eventually that sweat dissipates, it evaporates from your body, and you're good, right? You're cooled down, and that's exactly what sweat is for. All right. Now, some animals can't do that. That's not an adaptation that they've got, and they have other ways of dealing with increased body heat. All right. Give me 1 second, guys. All right. The third unique property that that water has is that it expands when it solidifies. Okay, that ice forms, and that formation of ice actually has a pretty drastic effect on life on Earth. And so we'll talk about some of the examples of how that is. Okay, I'm gonna be really dramatic about some of them because I think they're cool. I think it's cool to look at them that way, but also because you don't oftentimes think of ice in those terms. Water is oftentimes considered boring. Okay, so to discuss what happens when water does cool down, when water forms, liquid water forms solid ice. As water cools down, the molecules move slower and slower, and the hydrogen bonds no longer break. And so we've got to try to understand what's going on with water first, liquid water. When you see that kind of amorphous, I got a cup right here. That's Dennis Rodman, if you guys watched anything from the Bulls this summer. But it's got water in there, and it's amorphous. It's moving around. And what's happening with liquid water is that the water molecules that are in a cup of liquid water, when you move it around at room temperature, those hydrogen bonds are going to break and reform and break and reform very, very quickly. It's almost instantaneously. Break and reform, break and reform. The energy that's in the room temperature of the room, the heat energy that's in the room temperature of the room here, is enough to keep those molecules of water and the hydrogen bonds that interact between them, enough to keep them breaking and reforming, breaking and reforming. But eventually, if you cool the water down lower and lower and lower, the molecules of water are going to move slower and slower and slower. And so what happens to those hydrogen bonds that are constantly interacting between the water molecules is that they will ultimately just solidify. Those water molecules will move so slow that they will solidify. Okay? And so what happens then is we form this crystalline ice structure. One thing that I noticed that I forgot to do when I talked about hydrogen bonds the first time is discuss, kind of how those things happen. So I want to take that time in this blank space down here to do that. When you think about what a water molecule looks like, it looks like this. That's terrible, but that's technology. It looks like this, right? These two guys are water, okay? And then we've got another one. Oh, bugger, this is going to be rough. All right, let's do this. All right. Get done with that. Get a pen. All right. This one will keep it. There's a hydrogen. There's an oxygen. There's a hydrogen. Okay, so there's one water molecule. We're going to make another water molecule right next to it. Okay, kind of looking like this. Okay, just two water molecules, but I want to talk about hydrogen bonding and how these water molecules interact, because I kind of just skipped over it. All right, so the water molecule has the one end that is oxygen, and it is negatively charged. That's a negative. This is the negative oxygen on this one. All right. And it also has the positive charges of the hydrogens that we see right here. There we go. All right. And so when a water molecule that you see like right here interacts with another water molecule, let's say right here, it will cause a hydrogen bond to happen between these two areas. Okay? You probably already know this, but I want to make sure you've reviewed it and know it again. Know it more solidly, if you will. We know a little bit about electrical charges that opposites attract, right? So if this hydrogen has a partial positive charge and this oxygen has a partial negative charge, if they come sufficiently close to one another, they will have some kind of loose, weak attraction called a hydrogen bond, and that's what we see here. And so what's happening in the water, let's go back here, perfect. What's happening with the water is that those hydrogen bonds, because of movement, because of ambient room temperature, those hydrogen bonds are going to continue to break and reform, break and reform. As soon as they get close to another water molecule, they'll reform, and then they'll break and reform, or break and reform, okay? And as ice starts to cool down, it causes the molecules of water to move so slowly that those hydrogen bonds can now solidify. So as an ice crystal forms, it becomes less dense. It can actually float on top of the water. And so that's what we see right here in this picture, is the liquid water over here and the solid water here, the ice on this one. And one thing I always kind of do a Q&A, can you guys figure out what the differences between these pictures are? And one thing you'll notice, there's always like two main ones I try to suss out of you guys here. And number one is that there looks to be some kind of repeatable pattern here in the ice, okay? And that's what we would call a crystalline structure as compared to the water. Another thing that we can see the difference between the two is that there is more space between the water molecules here as compared to what we see in the liquid water. The water molecules over here look much closer together than they do here. And as a result, we get water, or a solid water, that floats on top of the liquid water. Now that doesn't happen in every, that does not happen in every single type of substance. In fact, it doesn't happen in many of them. For instance, here's one. Benzene is a substance. It's a nasty substance. We don't use that. But benzene, in its liquid form, if you put the liquid form and the solid form together, the solid form is going to sink. You think about anything else like that, right? If you take something like solid, you throw it in something that's liquid, oftentimes it's just going to sink. Okay, because it turns out that most of these substances in nature, when they become a solid from a liquid form, they become more dense instead of less dense. Now, I know that doesn't seem like a lot, but that is kind of a big thing. It's kind of a really big thing. It affects water below the ice. It affects all types of things below the ice. And so we'll talk about the significance of that here. One of the first things it does is, you don't think about this until it's pointed out right to you, it prevents deep bodies of water from freezing from the bottom up. Okay? Normally what happens, right? If we get a body of water, it freezes on the top and then there's still water below. Right? That seems common knowledge to most of us, and for the most part it is. We got to switch our thinking. What would happen if bodies of water froze from the bottom up? Well, think about it. Think about if we had like benzene and we had a brick of ice at the bottom, and then everything, once it froze more, it would stack up more and more. All the life that was in that particular lake or ocean or whatever, once the thing froze from the bottom up, all the life just sits on the top and dies. Okay, you'd have one winter in a lake, and all the life would be dead in it, because everything that was on top of it would be, everything that was in the water would freeze and be on top and just die, right? So it's one of those things we take for granted. Another thing that we don't think about very often is the chemical nature behind bond forming. Okay, one thing that's really neat to think about here is that as water freezes, hydrogen bonds form. Okay, and what do we know about when bonds form? Okay, even though hydrogen bonds tend to be relatively weak bonds, when bonds of any kind form, they actually release heat. Okay, and when bonds break, okay, I'm going to get something here. So let's say I take this. This is a just a popsicle stick. Let's say it represents a bond between my two fingers. For me to break this bond, I got to put energy into it, right? So heat energy is added, or energy is added to this to break it. Whereas the opposite, I've got to put a lot of, when I form a bond, the energy is going to be released. Okay? Breaking a bond, energy is added to break it. Energy released when I form bonds. Okay, so we think about this now. When ice forms on top of a pond, what's actually happening is heat is being released into the water below, which is kind of neat to think about. And if you've ever had fish, I had fish in this room once, and I'll never have them again because I changed the water one time, and the water was too cold, and I killed them. It took 5 minutes. They were like $40 worth of fish. There was like glow-in-the-dark ones. And I put water that was a few degrees colder into their fish tank. They weren't used to it, and they died. They died in 5 minutes. It was just, might as well flush them down the toilet, and I ultimately did. But what this process right here does, is allows for like a heat buffer. Okay, all of this ice that freezes on top of the lake is going to gradually warm that water just a little bit, not a ton, but just a little bit. It makes that cold shock on the animals that live in the water below it a little bit easier to handle. Okay, you don't want to cold shock an animal very, very quickly because they will die. All right. In addition, that ice layer on top helps to insulate the water below from the extreme temperatures that might be raging outside during a really nasty winter. On the flip side of that, as the ice melts in the summertime or the springtime, it absorbs the heat from the water. Again, it's just another way to kind of give this heat buffer, this gradual change in the water below, and the animals then, as a result, don't die because of temperature shock. Shock of the system of an animal because of the temperature is a very, very dangerous thing for an animal. And we'll see that pop up in other examples that we see later on in some of the other chapters. So the fact that ice floats and the fact that ice even just forms on bodies of water allows for aquatic life to exist underneath the ice. And obviously we see that. It's just, I hope you get a new understanding and appreciation for the fact that the reason that we still have life under the Arctic Ocean or anything that freezes, any lake or whatever, is because ice, solid water floats. And when the hydrogen bonds form in these crystalline structures, it releases that kind of gradual heat to the water below. And when that ice melts in the springtime, it sucks some of that heat out of the water and causes it to be these gradual temperature changes. It's kind of a fascinating thing to think about when you look at it from a different angle. Okay, these are just a couple videos. I'll link them. Anybody who's ever had a koi pond knows that life exists under the earth or under the ice. You can see the little koi swimming around in there, kind of fun. But I'll link those, and we'll just kind of leave it at that. The final unique thing or characteristic of water that we're going to go through is to describe the fact that water is a versatile solvent, oftentimes called the universal solvent. I'm guessing that a lot of you guys have heard that before. Pretty much every and all polar compound is going to dissolve in water. You've heard the term like dissolves like, right? Anything that's polar is oftentimes going to dissolve in other polar substances. Water is a polar substance, so anything else that's polar, like alcohol, is also going to dissolve in water. Non-polar compounds do not dissolve in water because they're non-polar. They are not like the polar nature of water, so like doesn't dissolve like. And so I want to make sure that you remember this and understand this, because this is going to come into play when we discuss cell membranes. Cell membranes and the polarity of cell membranes and things that need to cross over cell membranes to help a cell live are an extremely important part of cell membrane function. So remember that this is there. Remember that I talked about it. Remember I said remember this, if that makes any sense. All right. And so to talk about how water dissolves things, dissolves other polar compounds. Water attracts other ions in that polar compound and dissociates them. Okay, this is an important part of nerve conduction in our bodies. You see all sorts of different ions in our bodies. Contraction of muscles, calcium ions are drastically important in the contraction of our muscles. Sodium and potassium are extremely important in the conduction of nerve impulses. Those are all ions that are dissociated from the food or torn away from the food that we eat on a daily basis. And here we see digestion of food. Okay, and so what water does is the way that water does dissolve something is kind of neat, actually. If you see these red and white things, those are the water molecules, and here we see like a little cube of salt in the water, surrounded by the water. The negative side of the water, if I get my little pen out here, the negative side of the water, indicated by the oxygen, okay, that's a negative. Okay, here's another negative and another negative. That oxygen is partially negative, right? that negative end of the water is going to surround the cations that we see in the salt. Okay, so sodium is a cation, and we see that here these water molecules have surrounded the sodium molecule and kind of carried it away. All right? The same thing happens with the positive ends, okay, because opposites attract again. Here's a positive end, here's a positive end of the hydrogens. The positive ends of the hydrogens completely surround the anion, which is chlorine from the salt molecule, and basically tear it away, completely surround it. That's why we don't see those ions in water, because they're surrounded by other molecules of water. That's why oftentimes solutions look invisible. Okay, so that is how water dissolves these things. Now, when we see water do this type of thing, water does create what is known as mixtures. Okay, water creates mixtures seen throughout biological systems. So I'm going to spend a little bit of time here discussing the mixtures. Not much, but I only do so because mixtures are important because we see them all over the place. The first type of mixture is called a solution. That's where we see water create something known as an aqueous solution. Okay, where it completely dissociates some kind of chemical, completely dissolves some chemical that is in the water. And I bring this up because I just want to pinpoint pieces of vocab that we're going to use, the term solute and the term solvent. Solute is the chemical that is dissolved. Okay, so salt oftentimes, or like here Kool-Aid. The solvent is the chemical that others dissolve in. So the solvent in this case would be water. All right, move on to the next one, suspensions. Suspensions are important. We do see them all over the place. This is where substances are mixed in water but not necessarily dissolved. Oftentimes these might be really big hydrophobic molecules or nonpolar molecules that are suspended in the water. And they're important because we see suspensions all over the place. Blood is a really good example of a suspension. It's also a solution. That sometimes there are things dissolved in our blood, but it is also a suspension. It contains proteins and cells that flow through it in the plasma. Okay, and cells, cytoplasm. The cytoplasm is a watery-based material that contains organelles. Those organelles are suspended in the watery cytoplasm. Another thing that we see because of the solvency of water, the ability to dissolve things, is the fact that water can ionize. It can almost dissolve itself. A process by which electrically neutral atom or molecules are converted to electrically charged atoms. And so what we see happen with water is that it can ionize. It can create a situation, or there is a situation created where we have the hydroxide ion, which is this guy here. Okay, and we have something known as a hydronium ion, or just, if you want to think of it this way, the H plus ion. Okay, and these should look familiar because when you hear about the term hydroxide, you think to yourself, okay, that is something that's basic. And something that has extra H plus is something that is acidic. Okay, so the fact that water can ionize or turn or basically split itself apart into a hydrogen on one side and a hydroxide ion or an OH on the other creates the ability to make acidic or basic solutions. Okay, and so we need to know at least a little bit about the pH scale. We're not going to go crazy on it. It's basically just here to get you to understand that the relative concentration of hydrogen that we see here, if the hydrogen concentration is really, really high or high at all, or above 0 in a substance or a solution, it's going to be considered acidic. Okay, if it's really low, it's going to be considered basic. Or if the hydroxide ion concentration is really, really high, we can consider that thing basic. Okay, so the pH scale ranges from 0 to 14. You probably already know that. The pH scale has a neutral right in the middle number of 7. Anything from 7 to 14 is considered basic. Anything from 6.9 or 7 to 0 is considered acidic. Okay, and the more acidic something gets, the more hydrogen it has. The more basic something gets, the less hydrogen it has and the more hydroxide it has. Okay, so make sure you know that and be able to kind of apply it. Maybe know some of these very simple characteristics of bases versus acids if you want to go. No, never, I'm not going to do it. Not going to put that on video. But there they are if you want to know them. It's nothing crazy that you need to memorize or anything. Okay, but the importance of acid in as it pertains to life, and this ionization as it pertains to life, and one of the big ones is acid rain. Okay, these are two pictures show the effect of acid rain. Now, acid rain doesn't happen. It's not like you're taking 12 molar sulfuric acid and dumping it on trees. No, that's not what happens. Acid rain is generally a weaker acid, or it's a strong acid that's relatively dilute, or something like that. And this is a picture of the damage from trees over a very long time. Okay, a relatively long time of exposure to acidic rain, oftentimes seen in industrial areas. There's a very good chance that there was some kind of industrial plant somewhere in this wooded area or in this region. Okay, so some of those pollutants, some of those chemicals mix with the water in the clouds, and it falls back to the earth as acid rain. Again, this picture right here of the statue, this did not happen overnight. This did not happen in like some crazy acid rainstorm with 12 molar sulfuric acid and just melted this statue. This is damage that happens over years. Okay, it does not happen overnight. It does not happen in an hour. Acid rain is dangerous to ecosystems, and in this case buildings, because it is a continued exposure to a dangerous acid over long periods of time. Okay, and that can be a really, really damaging thing for you. Saw trees or water ecosystems. It can change the lake ecosystem. These fish maybe are used to living in this particular pH of water for the last 150,000 years, and then all of a sudden we come along and make acid rain, and it changes the pH of the water to 6.2 instead of 6.8, and that's enough to kill a bunch of fish. Okay, so acid rain, it works not by drastic nature, by drastic effect, but by the cumulative exposure over many, many years. Okay. Now, something that we can use here to minimize the shifts of certain substances between acid and base is something called a buffer. Now, I bring up buffers because there are many, many different types of chemical buffers in human bodies and living things, and they help to maintain our homeostasis. The normal pH of human blood is anywhere from 6.5 to 7.5, and when we start to get out of that range, we start to see that our body doesn't get happy. It's not happy. Okay. One thing that you might see a lot of in your everyday life is that you get headaches and you take something called aspirin, which is a salicylic acetic acid. A salicylic acid. That's it. I got it. A salicylic acid. And the main key term there is acid. And a lot of people who take aspirin eat it, and they get an upset stomach. They make this stuff called bufferin. Okay, and bufferin is basically aspirin coated in something that neutralizes that extra acid that the aspirin put into your stomach. So it kind of causes you to not have an upset stomach. It causes the shift in pH in your stomach to be less. Okay, it neutralizes this small amount of acid or base that the aspirin actually brought into your stomach when you took it for a headache. Okay, so our body has natural buffers in it. Sometimes we take bufferin or buffers like this to help our bodies feel better under extreme circumstances, but our bodies have some of these things naturally occur in them. Okay. This is a phosphate buffer system, and I like to point this one out because you're going to see a question almost just like this on your test. It's a very similar system. It works almost identically to the way I'm going to show you this one works, except it is like a different set of chemicals or something like that, but it works identical to what you see here. Okay. Now this is an equilibrium system, so you have to bring back some of your chemistry knowledge and figure out, okay, what happens in equilibrium systems with this double arrow, right? And that's the key to understanding this particular buffer system problem. The phosphate buffer system operates the internal fluid of all cells. That's this one right here. And if, let's say you eat something highly acidic. Let's say we've had people who have had their parents wash their mouth out with vinegar, which is a really weird thing. But if you've ever had your parents wash your mouth out with vinegar, vinegar's an acid. And let's say you actually drank all that acid. Or maybe you've got especially cruel parents that just make you chug vinegar for whatever reason. I don't know. But let's say you've ingested a fair amount of acidic solution and your body doesn't necessarily like it. What you've done to your body, let me get rid of the pointer. What you've done to your body, oh, you bugger, there we go, is you have increased the amount, put my arrow here. You have increased the amount of H plus on this side. Okay, so like we put a big arrow right in front of this H plus. We put a big arrow in front of that H plus. And so what this buffer system is going to want to do is try to get rid of this excess H plus that we put right here, because we drank a ton of vinegar for whatever reason. And so what happens is this extra H plus, so we put a ton in there, just put tons and tons of H plus in there, it's going to combine with HPO4 2 minus. So any extra H plus that we took in because our parents made us chug vinegar, right, is going to combine with this, and it's going to shift this equilibrium to the left, and it's going to create this stuff, H2PO4 minus. This right here is not dangerous. Extra H plus in our system is dangerous. So when we have an influx, a massive influx, for whatever reason, of H plus into this system, it's like we put a giant big arrow in front of here. When that happens, it means we've got a lot of extra of this, and we've got to find a place to put it. And where we're going to put it is we're going to put it with this molecule right here. Okay? And when we do that, we put that H plus with this molecule here. It creates this molecule right here and shifts that equilibrium to something that is not dangerous for you. That is how these biological buffer systems work. Now that's not a thing, a heuristic that you can apply to every single buffer system, but it's how these particular ones happen to work. Okay, that we're done. We're done with the giant hour and plus talk of water. I hope you enjoyed it. If you didn't, you can skip around to the parts that you did like. I don't know if you want to go do that. But this final slide here gives you some stuff to look at. It's the importance of water to living organisms. Kind of puts a bow on the entire talk. If you want to go to this slide and kind of use that as kind of a starting off point for your study, that's great. But I am going to end it here. Remember that when you watch this, write down questions that you have. I would like to have something to talk about when we come back to do our live sessions. Okay, so I'm going to get out of here. I'm going to let you guys get out of here. Inevitably, there's probably something I missed, and I'll try to fill in the blanks if I do when we meet next. See ya.